So today we're going to start lesson 5.2, verifying trigonometric identities. And I've written out the guidelines here for you as per the book. Page 357 is where we're starting. Verifying means that we're showing that two sides of the equation are the same. So we're not creating equivalent identities as we did. We're not simplifying. In 5.2, we're showing that the two are the same thing. So guidelines, we're only going to work on one side. Typically, we choose the most complicated. Choose the most complicated and work from there. Second, we're going to look for opportunities to factor, add fractions, square a binomial, create a monomial denominator. If the above don't help, convert all to sine or cosine and start from there. That usually makes things simpler. And if you're feeling like you're stuck, just try something. Go back to 5.1, look at those identities and see if you can convert. When verifying, this is what 5.2 is all about, you are proving that one side equals another. You cannot assume they are equal. You're trying to prove that. Therefore, you cannot add or subtract the same thing to both sides, as you cannot multiply or divide. So let's start by taking a look at example 1, page 358. Again, it says start with the most complicated. We can see the left-hand side of this identity is the most complicated. Secant squared minus 1 over secant squared is equal to sine squared. It says we're going to start by using a Pythagorean identity. Secant squared theta is the same as tangent squared theta plus 1. We still have this minus 1 on the end, and these two are going to cancel each other out. We're left with tangent squared over secant squared. And you can see in example 1, they're going to take secant squared and turn it into 1 over cosine. So dividing tangent squared by 1 over cosine squared leaves us with tangent squared times cosine squared, and we're going to rename tangent squared as sine squared over cosine squared, and we're still multiplying by cosine squared theta, and you can see that those cancel, leaving us with sine squared theta, and that was the identity that we were to prove. So take a look at these steps. Keep in mind that as you do more of these, they're going to become easier and easier and way more obvious. You guys go ahead and try problem number 15. Remember, try something and come back. So problem 15 says cosine squared beta minus sine squared beta, and we're thinking of Pythagorean identity right here, but we don't quite have it. We're going to take cosine squared and rename it as 1 minus sine squared. Then you can see we have everything in terms of sine. So we have 1, take away sine squared, take away another sine squared. We've taken away 2 sine squared beta, and we have completed our identity. It says, right here we are, 1 minus 2 sine squared beta. So we took the left side, the most complicated, and proved that it was indeed the same as the right side. Looking at example 2, it says combine fractions before using identities. So we see 2 secant squared, and I want to say alpha, but I don't think that's right. So we're just looking at this Greek symbol. First one to come up and tell me what that is gets a prize. I'm going to call it alpha for right now. So we can see on the right side we have the most complicated thing going on. We have 2 fractions. The first thing we want to do, the reminder from the first page of this lecture, was to add fractions if we could. So we're going to take the denominator and turn this into a fraction with a common denominator. We're going to multiply numerator by that, numerator by that. We end up with 1 plus sine alpha, 1 minus sine alpha on the top. And we can see that our positive and negative sine alpha will cancel out, leaving 2 on the top over 1 minus sine squared. And we're going to take that bottom, remembering our Pythagorean identity, 2 over cosine squared alpha, looking back to our original. We're going to change this into 2 times 1 over cosine squared, which we know to be secant. So 2 times secant squared alpha. And that's what we were asked to prove. Let's go ahead and try number 39, but before you get too excited, try not to faint when you look at that problem. Give it your best shot. Remember, we have 2 fractions. Let's try to add those fractions together. So on the get-go, we look at this and we think, oh my goodness, when will the torture stop? We want this to prove to be 0 because we have 2 fractions. We're going to go ahead and add those together, and in doing that, I need my first fraction to have the same denominator. I'm going to multiply top and bottom by the opposite denominator. I'm going to do the same thing, multiply top and bottom of the second fraction by the first denominator. So you guys can see, taking this cosine x plus cosine y multiplied by cosine x minus cosine y, we're going to go ahead and FOIL that, giving us cosine squared x. And if we have minus cosine y, cosine x plus cosine y, cosine x, those terms, of course, cancel. We have a minus b times a plus b. We know that that middle term cancels, and we're left with first term times squared minus second term squared. So we end up with cosine squared x minus cosine squared y. We're going to do the same thing, and you guys can see, without too much thinking, we have a plus b, a minus b. We're going to go ahead and multiply those out. We get sine squared x minus sine squared y. And that's all over. We don't need to do this, but we're going to. Sine x plus sine y times cosine x plus cosine y. And right now, in order to equal 0, we need that numerator to equal 0. So what we can see is this. From our Pythagorean identity from 5(1), we know sine squared plus cosine squared equals 1. We have sine squared x plus cosine squared right there. Sine squared x plus cosine squared x. And we're going to do this. We have a negative cosine squared and a negative sine squared. So we're going to factor out that negative, and we get sine squared y plus cosine squared y. And we know each of those to equal 1. Sine squared plus cosine squared, sine squared plus cosine squared, and what we get is 0 over our original denominator. We were to show that the whole thing equals 0, and we were able to do that without too much loss of skin or blood. Ew. So let's go on to example. So example 3 is asking us to verify this trigonometric identity. Of course, we're going to work on the left-hand side, way more complicated. We're going to show these two equal to negative tangent squared x. So both of these are Pythagorean identities, and we should have that sheet handy. We can see that tangent squared plus 1 is equal to secant squared. So we've done that substitution, and we know cosine squared minus 1 is the same as negative sine squared. So what we're going to do, we need a tangent. So let's go ahead. I know tangent is sine over cosine. I know that secant is 1 over cosine squared x. We're going to multiply that by negative sine squared x over 1. And we're going to get negative sine squared x over cosine squared x, which we know to be negative tangent squared. You guys go ahead and try number 47 and come back and yeah, they just seem to be getting worse and worse. But here's the neat thing: as you do more, you see more initially. So let's look at this one. We're supposed to prove the left-hand side is equal to 1. So the first thing I want to do, I know that sine squared plus cosine squared is equal to 1. If we factor out this negative, as we did right here, we get minus sine squared plus cosine squared. We can write that as minus 1. We just simplified that to minus 1. I took the first part of this. I saw 2 secant squared x in both of these terms. I see 2 terms here separated by subtraction. I factored out the 2 secant squared x, and I'm left with 1 in my first term and sine squared x in my second term. So I get 1 minus sine squared x, which happens to be cosine squared x, and we're going to multiply that by 2 secant x, which is simply 1 over cosine squared x. So in multiplying these two together, I have 2 times 1 over cosine squared times cosine squared. Those happen to cancel, and I get 2 minus 1 is equal to 1. 2 minus 1 equals 1. So in example 4, we're going to take one of the suggestions from the first page in proving trigonometric identities, and we're going to convert to sine and cosine. So let's go ahead and take the left side. They look similarly, equally onerous. We're going to take tangent x, cotangent x, and convert to sine and cosine. So we know tangent is simply sine over cosine. We know cotangent is cosine over sine. And we're going to take those and now add fractions. So I'm going to multiply each by the opposite denominator so that we can rewrite them with one denominator. So sine squared x plus cosine squared x, and that's all over our brand new denominator, that which we got by multiplying and combining the fractions. Cosine x, sine x. Well, we know the top to be a Pythagorean identity. We know that is simply 1. 1 over cosine x, sine x, and we can break that fraction apart, calling it 1 over cosine x times 1 over sine x. We know 1 over cosine to be secant x, and we know 1 over sine to be cosecant x. And that's what we were asked to prove. Let's go ahead and try problem 49 and come right back here. So 49 comes in a nice, neat package. We start with cotangent times tangent. Let's go ahead and change that to its reciprocal. 1 over tangent is the same as cotangent. Times tangent leaves us with 1. In the denominator we have the sine of x, and we know 1 over sine x to be cosecant x. This is part 1 of lesson 5.2. Part 2 will also be on Canvas, so come and watch those examples. And